did in the last lecture of reaction and diffusion that occurs simultaneously in a rectangular slab is something that you found a little hard. So what I'll do it today, before I go into the spherical coordinates or immobilized enzymes in the sphere, I'll try and recap once again what we did with the rectangular slab. So we're looking at this problem. Let's go to the transparency, and we're looking at this problem of the rectangular slab being here, and the enzymes are immobilized inside that rectangular slab. So these are impregnated, sort of encapsulated, and the length is the total length out in the direction in which the diffusion occurs is 2L. And what we are supposed to do is, this is a heterogeneous system essentially, right? But what we did was did a pseudo homogeneous approximation of it, right? So once we do a pseudo homogeneous approximation, we assume that reaction and diffusion occur simultaneously. So just recapping what we did. So just quick question: did any of you have any questions or doubts about what we did in the last class? About the concept? What your problem was with the concept, or your problem was with the calculations? Concept. Okay, so I'll run through the concept one more time. So the idea was that, here, let's go back. The idea was that when you have heterogeneous reactions, and say, for example, reaction in a porous catalyst, the reaction itself is heterogeneous, but when you look at it from macroscopically, from a large scale point of view, then you can assume the reaction to be homogeneous. Okay, what are the criteria? We discussed two criteria. One is that the length scale of heterogeneity over the macroscopic length scale should be very, very small. So in this case, for example, if I'm looking at a matrix like this excuse me, in which the enzyme is impregnated or encapsulated, the length scale of the pore over the entire thickness of the solid core. Okay, so this is the core, for example, or the total encapsulation. So if this length scale is L, say, or 2L, and the length scale of the pore is D, okay, the diameter of the pore, then D over 2L should be very, very small. That is my criteria number one, to be very specific. I said it in a little conceptual way. So that is, let me write it down also. So this is my encapsulation, the whole thing, and this length scale is L, and the length scale of a pore, for example, is, say, D, then D over 2L should be very, very smaller than 1, okay, for the pseudo homogeneous model to be valid. And what was the other condition we said? Yeah, so concentration CS minimum over CS maximum should be of the order 1. Okay, so there shouldn't be a large difference in variation between the maximum and the minimum concentration, because see, the whole idea is that averaging, what you're doing here is averaging. Now, what does average of any population signify? It means that somewhere, you're trying to have a sense of the total population by looking at the average. Now, if you have 3 people over there or 4 people over there, and so when you're taking an average out of 4 people, out of which the ages of 2 of them are, say, 5 and 6 years old, and the other 2 ages are 60 and 70, or 65 and 70, then you get an average of whatever, 20 or whatever it is. It makes no sense, because it gives you no sense of the population, right? So that's the concept here, that the maximum over the minimum over maximum concentration should be of some order 1. It shouldn't be very small number. So once we are able to do that, then we can substitute. So what we do is we average out this thing. So here we have the reaction. Let's go back to the reaction. So here we have the reaction. So this is the RR that you see over here, is the reaction at the small scale, at the scale of the pore. And if there is uniformity, more or less a uniformity in the concentration, and the minimum to the maximum pore scale size, minimum pore scale size over the macro scale size of the core scale is much smaller than 1, then we can do an averaging, which means that we take the reaction rate and integrate it over the volume and divide it by the total volume. Then you will get the average reaction rate, which is given over here as RV bar. Okay, so this is a basic concept. It should be okay right now, fine. So then we went over to the this particular example. So, once we have been able to do that averaging, what we have been able to achieve, we have been able to convert a heterogeneous model, which is much difficult to, quite difficult to solve, to a homogeneous model. We call it a pseudo homogeneous model because it is not really homogeneous, we are just assuming it to be homogeneous. So, once we have been able to write the pseudo homogeneous model, so then we can write a reaction rate as time, just like a homogeneous reaction rate, which is first order homogeneous reaction rate, Kv times C. And again, why are we doing first order? Because we are looking at the two asymptotes of first order and zeroth order, and the Michaelis-Menten kinetics is somewhere going to be in between this. I am going to come and show you actually how the Michaelis-Menten kinetics looks like, maybe if not in today's class, the first in the next class. So, once we have been able to write or assume a pseudo homogeneous model, then you simply assume that. So, once you assume a pseudo homogeneous model, what does it come with? The other assumption that diffusion and reaction can run parallelly. Okay. So, in reality, so what is the difference? The difference is this model that you are writing tries to mimic reality, but is not a direct actual representation of the reality. Okay. It's some sort of deformed representation of reality. So, in reality, diffusion and reaction do not occur parallelly, they occur in series, but when you convert them into a pseudo homogeneous model, diffusion and reaction can be assumed to occur parallelly. So, when you assume them to occur parallelly, then you can go back and write an equation of this sort that I wrote over here, d effective times Laplacian of C equals Kv times C. So, Kv times C being the reaction rate and the left hand side being the diffusion rate. What is there to note here is the d effective, because we are using a pseudo homogeneous model, the effective diffusivity is the sum total of the diffusivity through the solids part of the material and through the fluid in the pores. Okay. So, because you have different diffusivities, much different diffusivities actually through the solid and the fluid, and so if you had a simple fluid, the diffusivity would be much higher, whereas the effective diffusivity is going to be much lower than that because of the presence of solids. Fine. And then the solution was, I don't know if you had trouble with the solution we got by using the two boundary conditions. One is that at this extremity x equals plus minus L, actually shouldn't be 1, x equals plus minus L. So, this boundary and this boundary, you assume that concentration equals Kav times C naught. Okay, fine. And the other condition was that at x equals 0, del C del x equals 0. That comes from symmetry. We assume that it's because it's exposed to the same boundary condition on both sides, so we assume symmetry. Okay. One thing I want you to understand at this point is that you can have this equation, but if I had two different boundary conditions on two sides, for example, at x equals plus L, I had Kav times C1 or C naught 1, and then x equals minus L, Kav times C naught 2, then you cannot use a symmetry boundary condition, right? For symmetry, you need symmetry of equation as well as symmetry of boundary conditions. The other boundary condition should be symmetric, right? So, if you have the same slab and it is exposed to one kind of boundary condition, one kind of concentration on the left hand side, another kind of concentration on the right hand side, so of course, you cannot expect symmetry. So, in that case, how do you go and solve the equation? You do not have boundary condition 2. So, what did you do? Yes. So, the only difference is here you are solving for half the slab. Okay. But there you are not going to solve it for half the slab, you are going to solve it for the full slab, and the boundary conditions would be on both sides. So, you will use K naught C Kav C naught 1 on one side and Kav C naught 2 on the other side. So, there is not going to be symmetry. So, these are assumptions that you have to be careful about and shouldn't get too complacent about these things, because so I might give in the test, for example, I might give you the same problem with just two different boundary conditions on two sides, and do not assume symmetry. That will be very stupid of you to do. So, just be careful about what kind of boundary conditions are being used. So, then the solution of this is a very standard solution, which is a cos hyperbolic x and b cos hyperbolic y. But before we do that, what we did was we did the equations, turned the equations dimensionless, because it's easier for scaling, and when we turned the equations dimensionless, we got the dimensionless number Thiele modulus, which is KV L square over the effective. It's the ratio of the transverse diffusion time over reaction time. Okay. Why do we call it the transverse diffusion time? Because it's the diffusion time in the transverse direction. So, this is the transverse diffusion time Td, and you can have a diffusion time in this direction as well, which is typically known as Tdx, which is actual diffusion time. So, anyhow, so what would be the actual diffusion time? It would be the length scale L over here. If I am to write the actual diffusion time, the length scale L over here would be replaced by the actual diffusion length, right. So, we repeat again. So, TDR, if I call this is the transverse diffusion time, say this is L square over D, okay, D effective, and if I have a actual diffusion time, then what would that be? So, if this is my 2L and let us say this is my B, then that would be B square. Okay, not necessarily. This is D effective R and this is D effective X, because not necessarily the diffusion coefficients are going to be the same in the radial and the axial coordinates. Okay. So, these are things I want you to understand, because you know for example, the midsem are coming up, and one of the things I would like you to do when I give you a problem in the midsem is not to just pounce on the problem and solve it and get some numbers. That is not what I am looking at. What I am trying to look at is that how you approach a these systems that we are modeling over here, there are some intuitions, there are some assumptions, there are some understandings that come into the modeling. It is not just about pouncing on a system and writing an equation and solving it, because at the end of the day you might get a solution which do not in any way represent the system that you are trying to solve. So, what is important is to understand the system. For example, I gave you this example of the boundary condition being asymmetric, one possibility. The other possibility is if you have to consider both axial and radial diffusions, then the diffusion times might be very different. Okay, and it is possible there are problems when there could be encapsulations in matrices where the radial diffusivity could be very different from the axial diffusivity, or in other words, the radial diffusivity itself is varying axially. Okay, those kind of complications can come because these are matrices you make, and you can make them in certain ways. So, do you see what I am trying to say? So, the radial you have a certain radial diffusivity, but the radial diffusivity itself is varying axially, right, because the pore structure is varying the radial pore structure that you have might vary axially. Okay. So, anyhow, so we did that and we used x hat as x over L, my dimensionless coordinate, and theta as a dimensionless variable, c over kV c naught. Okay. And then my dimensionless equation became model became del 2 theta del x square equals phi square theta, fine. And then the solution is, this is what we wrote, and I think we wrote it slightly differently. We wrote it cos hyperbolic and sin hyperbolic, and got rid of the sin hyperbolic, we got just the cos hyperbolic. And then what did we do? We calculated eta, the effectiveness factor. So, the effectiveness factor is the reaction rate as it happens inside the matrix itself, which is a observed reaction rate, total reaction rate, actual reaction rate actually, not the intrinsic reaction rate, over the reaction rate, intrinsic reaction rate evaluated at the surface. Okay, that is how we had defined, if you remember, our eta. Yeah, so this was how we defined our eta, RV over RV evaluated at CS. Now, RV, general RV is much lesser because the concentration inside is much lesser. Now, if there were, this is something that you need to understand, if there were no diffusional limitations in the system, then your eta is going to be 1, right. So, because of diffusional limitations that occur in the system, what happens, your RV is decreased, because the concentration at any point inside the matrix is lower than that at the surface. So, because the concentration is lower, and this being a first order reaction, it is different. Now, what would you presume for a zeroth order reaction? This we discussed it in the different context in the last week's class, I believe. Eta will always be 1, right. Why is that? Because zeroth order reaction is independent of concentration A, and more than that, the whole idea of zeroth order reaction, as I told you, is based on the fact that there is plenty of substrate. Okay, if there is plenty of substrate, then the whole concept of mass transfer limitations does not come in at all, right. This is what we did in the previous thing that we did. So, eta is this, and as I told you, that tan hyperbolic phi over phi is what comes out. Now, what happens, one interesting thing that I asked you to do is remember this formula, eta is tan hyperbolic phi over phi. The reason being that this is a generalized formula. This is something that you can use, and how do you use this? There is a method called shape normalization. Have you heard of this? Shape normalization. So, shape normalization is essentially that if you convert, if you have any shape, be it spherical, be it cylindrical, be it some very weird shape, you know, the pentagon or some kind of weird shape, pyramidal, which you cannot capture. So, you cannot solve the equation in every shape, all of these shapes. So, what you do is you transform these shapes into standard shapes, okay, for example, a slab, and then you do all the calculations, and when you transform them, the only thing that is transformed is eta, for example, v square, for example, it goes as kv L square over d effective, right. So, that is your phi square. Now, this L square over here is your now your shape normalized length scale. Okay. You see what I am saying? So, this L square now, so in your definition of phi square, this is that correct, right, Lisa? Do you see? So, in the definition of L square phi square, the L that you have, the length scale that you have, is now a shape normalized length scale. Okay. So, which, for example, I will give you, next class itself I will show you what is r over 2 and r over 3 for cylinder and sphere, and so you can come up with what the shape normalized length scale is, and then you can. So, what is the idea is that irrespective of what form you have, you can transform it into a slab, right. So, is that a perfect answer? No, it is not a perfect answer, but the advantage is it is very close to the perfect answer. So, if you say that your eta is tan hyperbolic phi over phi, and you define your phi this way in terms of the shape normalized value, and there is a mechanism for that, r over 2, r over 3 for different shapes, this how this L is going to vary is given. So, what you can do, you can just use that value, shape normalized value of radius, and then use this formula. This is not going to be 100% perfect solution to your question, but you are 95% there in terms of your eta. So, the advantage is that if you do not, for example, if you want to use it as a for a formula in something and you do not remember it, you can just remember this single formula and then rescale your phi based on that, fine. So, this is I think where we stopped, and then I gave you this example of this. Now, two things I asked you to do. One was to be able to solve in the cylindrical coordinate. So, what is the solution of that in the cylindrical coordinate? I do not have, I think I have the pages over here. Yeah, I got the pages. So, this is the Bessel function solution you have, right. So, this is one form, if I remember, this is one form, or another form you can do also if you have this r square del 2 c del r square plus r del c del r minus phi square r square c equals 0. So, I can call my say y hat equals minus phi times r, okay. Then you can convert this to another form. Okay, let us call this not y hat, let us call this psi, just for the sake of simplicity. So, then your psi square del 2 c del psi square plus psi into psi plus psi square c equals 0. So, if I keep this and this over here next to each other, both are Bessel functions. They are just two different Bessel functions of two different kinds. Okay. What is that? One is Bessel and one is modified Bessel. So, you can use either form. So, what would be the solution? What would be the solution of this one? So, C equals, yeah, J naught psi plus B, huh? No, why? So, let us use up all the alphabets. So, this is the solution, and then the solution for this one would be, therefore, C equals some A hat, what would be? I and K. So, those are the okay. So, these two solutions are possible. So, either you write it in this form or that form. So, if it comes with a negative sign, then you have the I and K. and if it comes with the positive side then sign, then you have the j and y. Okay, it does not matter, the same thing you get. Now what after this? You have to evaluate the constant. So out of the two, so these two are eigenfunctions, I hope you know that. So out of these two eigenfunctions, these two here and these two here, what will happen? Which one? Which one? The b, right? In both cases, the b and the b hat would be 0. Why is that? Finite value at r equals 0, psi equals 0. So the problem is that, you know, both these, say y naught and k naught, they go to infinity as so this is my psi or r, psi or y, say. So as psi or y go to 0, they go to infinity. So those two are not allowed. So you can only have your solution in terms of j naught and I naught, and then it's simple because all you need to do. So if you have your solution as c equals, say, a j naught psi, then the other solution, if I remember, you have at psi equals 1 or something, right? Psi equals 1 is the other concentration that is given. Let's look at the screen here. Yeah, no, not this. Yeah, so we are looking, yeah. So this is the same kind of thing. So the concentration at psi equals 1 says some c naught. Okay, c equals c naught. Fine. So then you have, it's pretty straightforward. So a j naught 1. So you can just put in over there, and a would be equals c naught over j naught, something like this. It may not be psi over here. It may be psi may not be 1 over here. So even if its psi is at psi equals any value, you can put that value over here. So if psi equals psi naught, then you put psi equals psi naught over here. So very straightforward. Then you essentially, your final solution is c naught j naught psi over j naught psi naught. Okay. So this is the cylindrical coordinate. Now the other question we had was with the spherical coordinate. What is it? This is the solution equation. So I asked you to solve it. So what is the solution? So my equation is d effective r square ddr of r square del c del r equals kvc, and my boundary conditions are r equals d 0, del c del r equals 0, fine. So what do you do over here now? C? C times? C by r equals y. Now it should be, yeah, fine. So that's, yeah. So then what? What does it change to? You have done it or not done it? I asked you to do it yesterday. Come with
d2y by dr square minus kv by df y is equal to 0.
d2
Then
d2y
d2y by dr
square
minus kv by d effective y is equal to 0.
right.
So it can be solvable. Y is equal to c1 sin of h or something, and it is possible.
No, it is not cos. It is exclusion.
No, it's not cos, but at least this form is correct. So so okay, why, since none of you have done it and nobody has done it, right? You have done it, but nobody else has done it. So I'll do it here. So this is my equation over here is the effective r square del r of r square del c del r equals kvy. So let's call it f equals c equals f over psi. Is that what you said? Something different? Is that what you assumed? Yeah, but you said the other way around, I think, right? You can also get it that way. C by r equals some other variable. Okay. Anyway, you check that, but this is something that gives, I know. So my del c del r equals now minus f over psi square plus 1 over psi del f del r, or I mean I want to use a psi over here. So if I am correcting this, or let me just use another page. So 1 over, my equation that I am now trying to solve is 1 over psi square del psi of psi square del psi equals phi square times c. Okay, that's what I am trying to say, solve. And my boundary conditions are psi equals 0, del psi equals 0, and psi equals 1, and c equals some k v c naught. Okay, these are, what are these in these equations? These are in dimensionless form, right? So we started with the dimensional form, we converted it to dimensionless form, and my phi square in this case is going to be what? kv times big R square over d effective, right? So so now my assumption is c equals f over psi. So del psi equals minus f over psi square plus 1 over psi del c del psi, right? Done. Okay, so I go to the next one. So then my psi square del c del psi equals minus f plus psi into del c del psi. Okay, now del psi of this is this plus cancels out. So 1 over psi square del psi of psi square del c del psi equals 1 over psi times del 2f del psi square, right? So my equation now, so this equals this. Now this is equivalent to phi square of c, phi square times c, right? So what I get is 1 over psi del 2f del psi square equals phi square times c is now f over psi. So done. Okay, so my equation becomes del 2f del psi square equals phi square of f. So this is the equation that you've solved before, right? And the solution you know is cos hyperbolic and sin hyperbolic. Okay, so only thing that now left is a boundary condition. So my boundary condition earlier was psi equals 0, del c del psi equals 0. Now so which means that psi equals 0, del psi of f over psi equals 0, right? Which means that this is minus f over psi square plus 1 over psi del f del psi equals 0. Fine. Multiply all through by psi square, you will get minus f or psi times del f del psi equals f. This is a boundary condition, right? At psi equals 0, which means that f equals 0 at psi equals 0. Done. So this you get your first boundary condition. The second boundary condition is what was that? Psi equals 1. Yeah, psi equals 1, C equals KV C naught, which means that F equals again same KV C naught at psi equals 1. Now, your solution to your equation is F is A cos hyperbolic phi p psi plus B sin hyperbolic phi psi, right. So, first boundary condition was F equals 0 at psi equals 0 implies that A is 0, right. Done. Second boundary condition was this one, yeah. So, F equals KV C naught at psi equals 1. So, which means KV C naught equals B sin hyperbolic phi. If I remember right, last time it was my eigenfunction that remained was the cosine hyperbolic, right. This time the sine hyperbolic remains because of the boundary conditions. So, which means that B equals KV C naught over sine hyperbolic phi. That means my F is KV C naught sine hyperbolic So, this is my final form for F that we get. What is left now? We have to calculate what? Oh, yeah, converting into C is not a problem. So, C is F equals F over eta. So, which is KV C naught over psi This is straightforward. No, but what is left is we have to calculate our eta, okay, which was C, what is my definition of eta going to be now? C times yeah, C times 4 pi r square or psi square, whatever, this side from 0 to 1 divided by psi going from C naught KV, right, and the KV cancels out both places, numerator and denominator, the KV will cancel out, clear, because eta is reaction rate evaluated overall divided by reaction rate evaluated surface. So, the KV is in the numerator and denominator, cancels out, this is what remains, okay. Now, this is the denominator is straightforward, but the numerator is slightly tedious. So, what I will do is I will just give you the solution to this. So, my eta after I do all this calculation comes out to be 3 over phi, actually it is here. So, yeah, so I do not need to write this. So, this is it is here. So, eta comes out to be 3 over phi 1 over tan hyperbolic phi minus 1 over phi. Okay. So, what you see is that it essentially goes as cotan hyperbolic, the reason being that it goes as cotan hyperbolic, the reason being that the eigenfunction is changed from cos to sine, right. So, we now finish, we understand at least all the three how three different geometries how to do it, and as I said, so for you could be asked to do in any of these geometries using any of these boundary conditions. So, you should be prepared for that. So, A is the slab where the eigenvalues are. So, what are the eigenvalues for slab? Let us chart the eigenvalues. So, rectangular slab, what are the eigenvalues? Cos hyperbolic and sine hyperbolic, or it could be cos and sine, in which case for the, or in other words for the product, not necessarily for the product, if it is a if it is instead of taking part, let us see how can it be, how can there be a source term for the substrate. Yeah, maybe the substrate is produced from some other reaction. So, this is a freak case, but source term, let us say, but I just want to chart the eigenfunctions. Okay. So, this is the normal case and this is a special case if there is a source term. I just want to write all that. So, the next one would be cylinder. Cylinder would be J naught psi and Y naught or I naught psi and K naught, okay, depending on source and sink. Is that clear? Okay. And then what about the sphere? The sphere would be cos hyperbolic 1 over psi cos hyperbolic and 1 over psi sin hyperbolic, or it would be 1 over psi cos and 1 over psi sin. This is for a source term, special case. Is that clear to all of you? So, I am charting out all the three possibilities. So, rectangular slab is cos hyperbolic sin hyperbolic typically. If there is a source term for this substrate, it could be instead of a sink, it could be cos or sin, but special case again. Cylinder is J naught Y naught typically, or you can write it as I naught K naught also, and sphere is cos hyperbolic over psi and sin hyperbolic over psi. It could be cos over psi and sin over psi for special case where there is a source term. Okay. So, let us now go on to the next. So, is that clear? Is that clear to all of you? So, okay. Next, now go on to the next issue that we are looking at, and let us look at the screen here. So, till now what we did was, and this is a slightly more complicated form, a slightly advanced form of what we are doing. So, till now what we did was we looked at encapsulated matrices where the enzyme was entrapped only outside, and now we are looking at a more practical case where the enzyme is entrapped outside as well as inside the matrix. So, we looked at enzyme trapped outside or enzyme kind of covalently attached outside, then we looked at the case where enzymes were entrapped inside, and now we are looking at the case where both these things happen. So, enzyme is entrapped inside as well as is covalently attached to the surface, right. So, this is a slightly more complicated case. So, what do you think, what are your suggestions on what should be the equation on the boundary conditions in this case? Right. Equations will remain the same. The reason being that if you remember what we did before was that this does not affect the, this only affects the boundary condition. The receptors on the surface only affects the boundary condition, does not affect the equation, right. And the equation inside the matrix remains the same because reaction is occurring only inside the matrix. So, we are again back to the slab problem, and what you get is d effective del 2 C del x square equals k V times C. And what are your boundary conditions now?
Boundary is something CS.
It will be
Something CS that we have to solve one different equation in the boundary layer.
Yeah. So, there is a boundary layer, that is the thing that you have to say. What you said is not correct, but the equation is not correct that you said, but the concept is correct that there is a boundary layer. So, we have to account for that boundary layer and try and get the concentration across the boundary layer. And what was the mechanism that we followed in the last previously? We used the concept of mass transfer coefficients, right. We use the concept of mass transfer coefficients to calculate what would be my difference across the boundary layer, right. So, you do not essentially know what is your concentration exactly at the surface, but what you know is the concentration far outside the boundary layer, far from the surface, and you also know, if you know the mass transfer coefficient, you would know how much is the total driving force, okay, a total transfer, that would be the mass transfer coefficient times the outside concentration C naught minus C at the surface, right. Okay. So, that would be my boundary condition. Let me show you and then it will be clearer to you. So, this that you see over here on the right hand side, Kf C naught minus Cs, forget this term over here, don't worry about this term right now. So, let us look at this term alone, C naught minus C, okay. This is your total driving force, right. C naught minus C is the total driving force times the Kf, which is the mass transfer coefficient, that should be equal to the amount of flux that is coming in. fine. Now, what is this term doing over here? Because there are receptors on the surface. See, if the surface had no receptors and you just had a boundary layer, then this is what you have. But because there are receptors on the surface and there is a first order reaction going on the surface, you add that as well, because that is your consumption on the surface. So, whatever is coming in substrate, okay, or in other words, whatever is coming in equals what reacts on the surface plus what goes in. So, if you bring this to this side, for example, so then whatever is coming in is what reacts plus what goes in, fine. Is it clear?
Not clear.
Not clear? Okay. So, why don't we draw a picture and try and show? Okay. So, this is my matrix, okay. Now, the receptors are on the surface and the receptors are inside as well, fine. So, if the receptors are inside, then I straightforward write D effective del 2C del x square equals KVC. So, this is for the inside. So, governing equation for inside the matrix. Is it clear up to that point? Now, the boundary conditions. The first boundary condition is at this point, x equals L, let us say. So, what is happening over here is that if you are, so D effective times del C del x at x equals L should be equal to Kf C minus C naught, right, C minus C naught. So, this is nothing is happening, or in other words you can just write it like this, D effective times del C del x, x equals L equals Kf C naught minus C. That is how people write it, because C naught is typically larger than C. So, this is what you have. Is there any problem with this? No, absolutely not. Okay. Now, what happens, because the reaction occurs on the surface, okay. So, what is coming in does not all of it does not go in, a part of it is actually reacting on the surface, okay. And how do you incorporate that? So, take that out, what is reacting on the surface, which is the Ks, surface reaction rate, times C at x equals L, okay. Is it clear now? So, this is without what is happening on the surface. So, this part, let us put this over here. So, what is coming in here through mass transfer is equals what is going out, but that is not the reality. In this case, there are receptors on the surface, and a part of what is coming in is actually reacting with what is there on the surface. So, you have to take that out. So, what is coming in minus what reacts on the surface is what is allowed to go into the matrix, okay. Okay. So, that is my BC 1, and BC 2 is again the same, the straightforward BC, which is x equals 0, del C del x is 0. The reason being that again there is symmetry. So, all around you assume the same boundary condition. So, all you need to do is go ahead and solve it, but before we do that, we are going to make this equation dimensionless, okay. So, we have to write the equation in dimensionless forms, and we have to define some dimensionless variables. And can you tell me that last time we had one dimensionless number, right, two dimensionless variables which are x and theta, and one dimensionless number which was a Thiele modulus. In addition, do we have another dimensionless number this time? Yes, we have. And why do we have another dimensionless number? Because of Kf. Because see, dimensionless numbers are always quantitative of the physical phenomena that is happening. That is the way you have to look at it, not in terms of coefficients and so on. So, earlier what were the physical phenomena that were there? Earlier case, what was the physical phenomena that was there? The diffusion and reaction. So, you had phi square, which was a ratio of diffusion time over reaction time. Now, what you have? Diffusion, reaction, and let us call this Tm, external mass transfer, okay. So, these three phenomena occur simultaneously. So, you will have therefore two dimensionless numbers. One would be, say, a ratio of, so out of these three you can get any two independent dimensionless numbers. So, it could be Td over Tr is 1, and then you can have say Tm over Td, which is I will come to that. So, typically these are the two numbers that are used. One is the ratio of the diffusion time to reaction time phi square, and another one is the ratio of mass transfers. So, here for example, what you have is this is a external mass transfer and diffusion is internal mass transfer. So, what you have is another number which is the ratio of external to internal mass transfer. Okay. In addition, you can form another number actually, because you have surface reaction, and the rate for surface reaction is going to be different from the rate from the reaction inside the matrix. Why is that? Because inside the matrix it is a volume average rate, whereas the surface reaction rate is the intrinsic rate based on the surface reaction rate. So, you can form another number there. We are not going there, but there is a possibility. Okay. So, let us look at what we have over here. So, we have theta, which is C over C naught k V, okay, x hat, which is x over L. We have phi square, which is k V times L square over d effective, and then we have this quantity Biot number, which is the ratio of intraphase mass transfer, or in other words internal mass transfer time over interphase mass transfer, in other words external mass transfer time. Okay. So, this is a new number that we have, and you have studied this number elsewhere, but we just get back to it here. So, phi square is your ratio of transverse diffusion to reaction, or interphase mass transfer to reaction if you want, and Biot number is the ratio of intraphase mass transfer to interphase mass transfer, in other words internal mass transfer time over external mass transfer time. Okay. So, if your internal mass transfer is very slow, then as compared to external mass transfer, which is typically the case actually, then what will happen? Biot number is much greater than 1, and if your external mass transfer is very slow as compared to internal mass transfer, does not happen typically, then your Biot number is much smaller than 1. Okay. And so, you have three different competing phenomena that are occurring over here, and the surface reaction we are not considering here because it's only few receptors are engaged at the surface, and the major reaction is occurring at the inside. So, you have the ratios of these three numbers. So, let me simplify for you. Phi square equals T d over Tr, which is internal mass transfer over reaction, and Biot number is Td over Tm, which is internal mass transfer over reaction. Okay. So, which means that phi square over Biot number would give you the ratio of, it is not reaction, this is external mass transfer, give you the ratio of external mass transfer over reaction. Clear? Is clear to everybody? Okay. I am not, we are again running short of time today. So, so I will go through this quickly a little bit, and then one of the things I want you to do is actually go and look up your notes. So, if there are problems, I will explain at the beginning of the next class like I did today, but I do want you to go back to your notes and have a look at it. So, when I write in terms of these two dimensionless variables and these two dimensionless numbers, my equation that I had before comes out to be the same, del 2 theta del x hat square equals phi square times theta. Boundary condition is x hat equals 0 del theta del x 0, and this boundary condition over here is x equals plus minus 1 del theta del x hat equals Biot number 1 Biot number times 1 minus theta. Okay. Okay, who will tell me? Krishna Pratap, you will tell me that is the boundary condition, second boundary condition, completely correct? Right. So, this boundary condition had been written without the reaction into consideration. So, you get del theta del x hat equals Biot number into 1 minus theta at x equals 1. If you have a reaction term, it does not make much of a difference. What happens is you just put a gamma out here, okay? Because the reaction term, if you remember, also has the external boundary condition, which is that x at x equals 1. So, basically what you have is this. So, you can add your gamma over there, and then gamma will have the Ks over Kv and so on. So, just a factor over there. Okay, is it clear? Let me go back and show you, then it will be clearer. Again, here, if you look at this equation, this is kf c naught minus x at plus minus 1, okay, minus ks times x at plus minus 1. Okay. So, you can club, what I am trying to say is this and this are two same variables, and you can club these two same variables. So, what you will have is d effective del c del x equals kf c naught minus kf plus ks over kf c at x equals 1, right. Fine. So, this number is your gamma, that is all I am saying. So, gamma equals kf plus ks over kf, right. So, in the same, I have this boundary. So, so in dimensionless coordinates x equals plus at x equals plus minus 1 del theta del x hat is Biot number times 1 minus gamma, where gamma is kf 1 plus ks over k. Yeah. So, that would not change your solution or any of these things, just the boundary condition will be slightly altered. As a result, your constant would be slightly altered, but otherwise it would not change anything else. Okay. So, as we do not have a lot of time today. So, let us quickly summarize this. So, we did this and there is no reason for us to repeat. So, theta equals a cos hyperbolic x plus b cos hyperbolic sin hyperbolic phi x. So, there is no reason for us to repeat. So, del theta del x would be 0 at x equals 0. So, b would turn out to be 0 and theta would be this, and all you need to do is apply this boundary condition at this end, okay, and you will get your solution. So, I did this without the gamma out here, but you can just put the gamma in there and it would not make any difference to your equation. So, this would be your theta that you get at the final thing, but again without the gamma, and if you put the gamma in here, if I remember, yeah, so it will come over here. The Biot number would come with a suffix of gamma. Okay. So, it will be Biot number times gamma cos hyperbolic x and this. So, what I want you to do is just go and redo this and see where the gamma comes in. I am sure it comes in over here, but just for you to check. Now, so this is, once you write it in this form, then you can write it in the tan hyperbolic form as well, because sin hyperbolic over cos hyperbolic, and then you get the tan hyperbolic phi over tan hyperbolic p and so on, and these are values at x equals 1. So, this is general theta and this is evaluated at x equals 1, the surface concentration, fine. Now, why do I do that? Because I need to evaluate the eta, the effectiveness factor. So, I just need to evaluate that. So, my RV, the average volumetric average, is given by kV over L times integral of this from 0 to 1, okay, which is the integral of this. Is a little complicated integral, and then eta comes out to be tan hyperbolic phi over Biot number tan hyperbolic phi of plus 1. This is what it comes out to be. This is because RVCS is this number. So, this gets cancelled with this over here, and this is what remains. So, I think we are doing it probably a little fast today. So, I would stop here, but I think probably we might. Is it clear to everybody, or do we need to go back to it at the in next lecture? What I want you to do is just go back and put this gamma over here that we had here. Okay, there is a gamma out here. So, you just, and as you see that my intuition tells me that the gamma comes here with the cos hyperbolic term. So, wherever there is a cos hyperbolic term, the gamma would come there, okay, and then you can just, then the rest is easy, but again this integrals are not very easy, that's the problem. The integrals are actually not very difficult either, because it's just cos hyperbolic. So, the denominator is something you don't need to worry about. So, this is just cos hyperbolic, the integral of that would be sin hyperbolic. But we the thing is that we can't really go through each of these steps in this class. So, if you want, it looks like I still have a couple of minutes. So, if you want, I can go through this. So, theta equals Biot number cos hyperbolic phi x times phi. I guess the gamma would come here, okay, here and here, okay, that's my guess. So, if you do that, then integral of theta dx hat would be simply Biot number gamma over this entire denominator. I am not writing it because of lack of time. Integral of cos hyperbolic Cx dx hat from 0 to 1. Okay. So, which would be this whole thing in square brackets over 1 over phi sine hyperbolic phi once you put the integrals out there, right. So, so what you get is your eta comes out to be tan hyperbolic, because the sine hyperbolic and the cos hyperbolic you can take there as a denominator, tan hyperbolic phi over, because there is a phi out here, so that would come. Okay. So, phi times phi over Biot number tan hyperbolic phi plus 1. Okay. So, what I want you to do is, as homework today, is to go and add the gamma and go through these steps, because unless you go through these steps yourself, this is not something that you will take away from the class. So just go through these steps, because as I said, in the test, for example, you might have to do all these calculations very quickly within a short period of time, and there is only one way of being able to do that, which is do them yourself. So I want you to go through these steps, and if there are problems, I'll recap that in the first 5 minutes of the next class. Otherwise, I'll start with something else. Okay. So I'll stop here. Thanks.